Effectively testing and validating your strategies prior to going live requires data. And now more so than ever, with the proliferation of machine learning and ever more rigorous tests and validation methods, the amount of data that our models consume is growing at a somewhat exponential rate. Oftentimes you're ingesting gigabytes or maybe even terabytes of financial data whilst testing out different strategies and models. And the most common method of retrieving financial data is using a REST API, especially for historical data, and making thousands of subsequent GET requests in order to access all the data that you need. And so in this video, I'm going to show you how you can use AsyncIO to very quickly 10x the speed at which the data downloads from your provider. Now, this does require an unlimited subscription to a data provider. The exact provider doesn't matter. The methods I'm going to be showing you here are very general and they can be applied to any sort of code dealing with a REST API. In this video, I'll be using Polygon simply because it's very cheap, easy to access, and I know a lot of people use it as their primary data provider as it lets you do unlimited requests. So what I'm going to be doing over the course of this video is I'm going to be grabbing the 1 minute bars for a period of several years over many different tickers and using the queue object from AsyncIO, I'll show you how we can significantly speed up the acquisition of our historical data by a factor of at least 10. So without further ado, let's dig into a Jupyter notebook that I have open here. So this is the code that we'll be working with during this video. Don't get too hung up on the exact details of what's happening. If you've ever seen any one of my tutorials before on how to gather data from an exchange or from an external data source, broadly this is exactly the same. We have our API key here, our URLs. I want to gather data starting on this date, ending on this date, and I use some pandas wizardry here to extract a list of all of the months between those two dates. So I have one element for every single month, and that's because each request on my end is 1 month long. This of course will depend on your data provider and the granularity of your data. Basically just set the time range so that you can request the maximal amount that your provider will give you at once. So if you're after more granular data, like maybe trade data, that might just be 1 day. But for minutely candles here, we can request a month at a time fairly comfortably. So these are all the timestamps we're going to request. We're going to request data for each of these months. And then this is the function that does the work here. So you just give it a symbol. So I could give it Apple, for example. And I give it a month. So I could give it the 1st of January 2021. And it'll request all of the data from January. Very, very simple using the requests library here. We build the URL as per the Polygon specification here, just using the standard API parameters. I do some processing of the data. I make sure that we actually retrieve some data, that we've got at least 1 bar, and then I save that down to a CSV. So let's just run this and see what happens here. So I'll pull up the folder here, so this data folder. There's nothing currently in it. Let's go and run this cell. And as you can see, it requests January, February, March, April, so on and so forth, one after the other, at a rate of maybe 1 per second there. Now, what I can do is I can open up HTOP here, and if I look at the processors consuming most of my CPU, you can see it's only taking about 10% of a single core. So this script really isn't making efficient use of all of the processing power I have at my disposal. And as a result, this is going to be really slow. So this is just for Apple data, remember? Depending on the size of your database that you want to populate, how much data you need, you might need to do this for all 10,000 stocks that are currently available in the US. And that would be very, very painful indeed if you had to proceed at this rate. You'd be leaving it running for maybe weeks on end and just hoping it didn't fail during that time. And it's especially frustrating if you immediately need that data in order to start working with your model and making sure everything works. So in the next 10 minutes or so, I'm going to show you how you can transform generic request functions like these that just deal with basic REST APIs into an asynchronous function that's going to pull that data at least 10 times faster. As I mentioned earlier, don't get hung up on the particularities of this code. You might be getting data from Binance or from FTX or from a different provider. As long as it's a REST API, the techniques I'm about to show you here will work just great. So the first thing that we'll want to do here is to transform this function into an asynchronous function. So currently it takes in the symbol and month, and then it downloads that data and appends that to a CSV. And it does that all sequentially, one step after another. The problem with that is that during this request here, when we're asking for data from Polygon, there's roughly a 100 to maybe 200 millisecond lag here, where the computer's not really doing anything. It's not having to process any data or save any files or anything. So really, it could be doing other jobs during the time it's waiting for a response here. And that's essentially what an asynchronous function allows us to do. We can use some special syntax to say, when you get to this point, if you're just waiting around, feel free to go do something else and come back to this function later on. Now it's relatively simple syntax here, so you just do async def instead of a regular defined function. And then instead of using the requests library, you want to use HTTPX. So you'll notice I imported that at the top there. It's a very lightweight library, easy to use, and the syntax is almost exactly the same as requests. So all we do is we move our request up a little bit, we just indent it there, and we use the context manager provided by HTTPX. So it's async with httpx.async client as client, and then instead of request.get, it's simply client.get. Now remember what I said earlier, we want to signal to Python that at this point, it should go do other things and wait until this function has finished, until we've got the data, and then it should come back. And the way we indicate that to the interpreter is we use await here. Just a special keyword, you may have seen that one before. And so that's actually all of the modifications that we need to make to our basic REST function here. It's pretty much you add an async before the function, and you add this little context manager with an await in there on each one of your GET requests. That's the only modification you need to really make to the body of your request, whatever your main request code that you're using now is. So let's go ahead and test out this function, make sure everything's still working. So I'll run the cell, make sure everything loads, and then we'll load up a new cell, and we'll run this function. So I'll go grab it. So it's download month sync, and then we provide a month. So a symbol, well, let's just do Apple. And the month, I believe I have a variable called start month, which is just whatever the first date is here. And if we run this, you'll see we just get this weird coroutine object download month sync at memory address. And so we see that async functions don't behave exactly the same as what our regular Python functions would do. Were this a regular Python function, it would just run straight away. But because it's asynchronous, we need to add this extra syntax in here, and we need to say await download month sync. So run that. You see that the cell actually ran there, and I guess if we check the file here, I didn't actually print anything out. you can see there's an apple.csv. If I delete it, run the cell again, the CSV appears there. This await syntax here only works in Jupyter or IPython, so if you're working in Spider, it'll be quite similar. If you're using Visual Studio Code or a similar program, or using Vim like I normally do, in that case, you'll want to use AsyncIO.run, and then the same sort of deal. That's just an implementation detail depending on your environment. If I try this on here, I'll get an error. It'll say AsyncIO.run cannot be called from a running event loop. And I believe that's because Jupyter and IPython use AsyncIO under the hood, and you can't have two separately running AsyncIO processes. You can only have one event loop running at a time, as we see here. So just bear that in mind. Depending on the environment that you're in, you'll either want to use the await syntax that I'm using here, or AsyncIO.run to run whichever function you'd like to run. So that's all well and good here, but we don't seem to have won anything at this point. We're pretty much in the exact same situation as before, except we've added some slightly complicated syntax that's a bit strange. So how do we actually leverage this and get the sort of 10x that I promised earlier? Well, what we're going to do is we're going to make a function called main. And this function is going to be responsible for creating a bunch of different tasks. So a task is going to be a particular data set that we want to download, and it's going to be an asynchronous function, async-def main. Going to take no parameters in here. And what this function is going to do is we're going to create a queue object. So queue, always difficult to spell, is equal to AsyncIO.queue. So it's this one in the documentation that I referenced earlier. It's a first in, first out queue, meaning that you can put objects into it, and the item that was put in the longest time ago will be retrieved from the queue. So what I'm going to do is I'm going to go for every symbol that I want to check here. So for every symbol that I want to download, and for every month of data, so for month in all months. So remember that list that I had earlier. This has got every single month of data that I need to download. For all sims and for all months, I want to add a task to this queue. So queue.put no wait. And the item I'm going to add is going to be a tuple, and it's going to have the sim and the month. And that's basically going to represent one job or task that's going to be executed in this function. So these parameters are going to be passed to this function for every single one of these tuples that we've added to the queue here. Okay, so we've got this queue, and it's full of different jobs that we'd like the system to run for us here. How are we actually going to run those jobs? Well, in order to do the jobs, you'll want a worker process. And a worker process is going to take one of these jobs, it's going to execute this function, and then it's going to get a new job and execute that function, so on and so forth. And while one of the workers is waiting for the data to come back to it from Polygon, so while it's in this await here, the other workers can get on and send their requests or do any processing that they need to down here. The worker code is relatively simple. I'm in fact basically just borrowing it from this documentation page here. It's down at the bottom. You can basically just copy and paste this, but I'll type it out for fun here. So async def worker. And I'll pass in the queue object. And on an infinite loop, what I want to do is I want to get a task from the queue, execute the task, and then repeat that forever. So params here is equal to await queue.get. This function here is asynchronous because the queue might not be able to give us a task right away, so we have to await it here. After we've got our parameters, well, I want this worker to execute our function that we had before. So that's going to be using the await syntax here. It's going to be await download month synchronous. So I'll paste that function name in here, or maybe I should rename it now. It's actually asynchronous, so I'll just rename that. And then we're just passing the params here as before, so I can unpack this params tuple here. So remember, this is just a tuple of 2 items, sim and the month, and I'll unpack them using this star, and that will pass them in to the function here. Again, this is an asynchronous function. We have to await it. This will actually be the same whether or not you're on Jupyter. It's only for the execution of an asynchronous function outside of a function do you have to use this particular syntax. If you're inside a function, it's always going to be await. Okay, so we get the parameters, we execute the job, and then we need to tell the queue that the task is done. So it's just queue.task_done. And then the loop will run again, and it'll get a new job, and it'll repeat that until it runs out of jobs. Now all we need to do is boot up a bunch of these worker processes. So let's create a list here of all the different worker processes that are going to be running. So we'll do tasks is equal to an empty list, and then we'll populate the empty list with a bunch of different workers. So for I in range, give it whatever number you want. I'll give it 3 to start with. We'll then create a task here. So a task is going to be equal to AsyncIO.create_task. What task do we want to do? Well, you can pass any asynchronous function in here. So I'm going to pass a worker, and you need to provide the arguments to it as well. So that's going to be queue. That's the only argument it takes in. It takes in this queue object. And then I'm going to append that task object to the tasks list here. So tasks.append task. So this AsyncIO.createTask is going to tell this worker to get going. It's going to make a new task run in the background. And we're keeping track of all the different processes here so that we can make sure they cancel when the Python program finishes and we don't have any weird memory leaks or processes going on in the background. But first we need to make sure they've actually finished here. And to do that, use another await here. So it's await queue.join. What that's going to do is it's going to just wait here until the queue is empty. And the queue is only going to be empty after all of these tasks have been finished. Because after a task is finished, it's removed from the queue. So these workers are just going to keep beavering away until they eventually finish. After the queue's empty here, we'll want to cancel all of our tasks that we've created. So for task in tasks, task.cancel. And then in order to make sure that they actually cancel, we need to wait until they're finished canceling. And I'm going to use AsyncIO.gather to do that. So we can unpack the tasks here. And then gather will only unblock once all of the tasks are completed. So this here is basically the completed framework of how things are going to work. So I'll run these 2 cells, and then we need to just run the main function here. So I'm going to run main, and I'll provide a list of sims here. So sims is just going to be, say, Apple for now, but we'll add a few others in a second. Again, this is outside of a function. So if you're using await outside of a function, you can only do that in Jupyter or IPython. In any other Python environment, you'll want to do asyncIO.run and then main, like this. Just depends on your environment that you're using. So let's run this here and see if we get any errors. Looks like no errors so far, which is ideal, although it's taking a little bit of time to run, so I am suspicious. There we go, it did indeed finish, and it just gave me this cancelled error. I think if you want to get rid of that, you just have to do return exceptions is equal to true. Let's try running this again. So that looks like it ran great there with no massive issues. What I can do here to make things clearer is I can print out the parameters here. So print assigned job, and then I'll print out params. So every time a worker gets assigned a job, it'll print them out, and that way you can see things running in real time. So 3 of them there were running at once, and this is moving significantly quicker than it was before. If you remember right back to the beginning of the video, I'd say this is maybe double the speed. We're using 3 workers and we get roughly double the speed. It's not going to be exactly linear because there's lots of tasks that need to be done synchronously, like data processing, but it's still pretty good. So let's crank up the number of workers here and see just how fast we can get this to run. So if I run this to 10, you can see that's pretty speedy here overall. It finished very, very quickly. If I run it again, it finishes in just a matter of a few seconds really, compared to 30 seconds plus on our initial attempt. One thing I will caution on here is if any of these jobs, so if this function throws an exception at some point, the function's going to get stuck in an infinite loop and it'll never be able to empty this queue because it'll just throw another error. It'll try and accomplish this job here, it'll get thrown an error, and it'll try again, but then the error will throw again, and this queue will never be emptied, which means your function will never stop running. The way to get around that is to properly handle your exceptions here. So a simple way of doing that would be to just go in here, do a try and accept. So try, accept. Accept will print out the exception here. So exception as E. We'll print out the parameters that were used and the exception. And then we'll make sure that the task is marked as done. So even if it fails, the task is still going to get marked as done, which is going to remove it from the queue, and therefore the queue will be able to finish. You might want different behavior. You might want it to try again or to just completely error and break. That's up to you how you handle your errors here. Just something I thought I'd flag. It saves you chasing down very, very minor errors here, because if you don't handle the exception, the queue will just keep running forever. And so we can give this a further test here. So I can add a few other symbols in. Maybe I'll add Tesla or Google or Meta. And I'm downloading 3 or maybe 4 years here of minutely data for each of these sims. And you can see how blazingly fast it runs here. It's at least 10 times quicker than it was before. And if it's not, you can crank up this amount of workers here until your CPU is sitting at close to 100% here. So you can see it's now running at more like 65 to 85. It's making much more efficient use of the resources it had before. And you can see it looks like that's finished already, downloading those 4 different bars. One thing that I'll quickly caution on here before I end the video is that because these asynchronous functions are directly saving down to CSV, we're not guaranteed to have all of the data saved down in the order we requested it in the queue. So it's very possible for data from 2018 to be after data from 2019 due to the order of the requests and how that worked out. If that's a problem for you, you can of course just load the CSVs, sort them by date, and then save them back down. That's not a very big job. Not that difficult to write a script for something like that. And so that's it for this video. I hope you've learned something about AsyncIO. Maybe it seems a little bit less scary right now, and you can easily use it in your projects to massively speed up the time it takes to acquire gigabytes and gigabytes of data so that you can train your models faster and speed up your strategy generation process. So I hope you enjoyed the video, and I'll see you in the next one.